Okay, we're continuing our journey with AI basics. Let's recap our journey so far. 2 segments ago, in segment 14-15, you built your first CNN from scratch. A cat versus dog classifier. It worked okay. You achieved 80 something percent accuracy, but then we discovered the problem, right? When we showed our model a fox, it couldn't handle it, right? Because it only had two output buttons, cat and dog, and no fox option. We call this a fox problem. To add foxes as a third class, we need to collect many more images labeled with the foxes and retained from scratch. Uh, that's expensive and time consuming. So in the last segment, we learned the theory behind the clever solution, transfer learning. We discovered that neural networks trained on millions of everyday images, like Google's mobile net version 2, trained on ImageNet's 14 million photos, actually learn universal features in their early layers. Edges, textures, shapes, patterns. These are useful for any image task, whether it's cats, cars, or X-ray, CT, MRI. We learn that we can freeze these early layers and just retrain the final layer for our specific task. So we use the earlier layers as they are, and then we add other layers. And we even previewed the Keras code, where the base model trainable equals false. Okay, so today we put all of that into practice, but with a twist. We always have a twist, right? Instead of adding foxes to our cat and dog classifier, we're going to tackle something even more exciting, totally different: medical imaging. Imagine you spent years of learning to recognize everything in the world: cats, dogs, cars, trees, faces, buildings, millions and millions of images. You become an expert at understanding what you see. Now someone asks you, can you look at these medical x-rays and tell me which ones show healthy lungs and which ones don't? Do you need to forget everything you learned and start from scratch? Of course not. You already know about shapes, edges, textures, and patterns. You just need a few examples of what healthy versus unhealthy lungs look like. This is transfer learning. And today we're going to see in action with actual medical images. But here's the twist. We're also going to discover something surprising. Sometimes when you have very little data, the fancy deep learning approach isn't the best choice. We'll compare two completely different AI approaches and see which one wins. Here's an important disclaimer. Before we start, I need to emphasize that this is an educational demonstration using AI generated X-ray images. The AI generated these X-ray images. So I'll show you some of the images shortly. This must never, ever be used for real medical diagnosis. Real medical AI requires thousands of validated clinical images and regulatory approval. Okay, so do not think that these x-rays are real. They are all for demonstration purposes. So on our first cell here, as we know by now, we import all the necessary libraries like NumPy, Matplot, TensorFlow, and then PIL, the Python image library, and so forth, and sklearn, and we even have something new that you've never seen before, support vector, right? So we're going to have that, and then so we import all these, and these are going to be helpful to analyze lung images, X-ray images. Okay, so you copy, paste, and run this code, and then it will download. It will download 10 normal and 10 abnormal images. That's only 20 images. This is tiny for deep learning. Remember, ImageNet has over 1 million images. Can we really train on an AI with just 20? Not really, but let's find out how much we can accomplish with just a few images. Okay, so we download them. It's only 27.7 megabytes. Okay, and then cell number 2, when you copy paste and run here in Google Colab, let's explore the images. You can see the normal lung x-rays, and these are abnormal lung x-ray images. I'm not a doctor, I don't know, but AI said that they are abnormal lung images. I can see some big like circles. It's like a hole in your lung. Probably this is because it's AI generated. The real images would have different kind of dots or some white spots, and then when doctors see them, they will be able to tell what the problem is. So so see the cloudy, lighter patches and weird circle spots? Those white or gray areas could represent fluid, infection, or other problems. This is exactly what the radiologists look for. These, again, images are AI generated for educational purposes, so the differences are a bit exaggerated, and real x-rays require years of training to read accurately, but the principle is the same. We're looking for patterns that distinguish healthy from unhealthy. If we have accurately labeled images and lots of them, we can be a little more real than this. But for now, this is just for demonstration purpose. Okay, so let's go over the key concepts. There's a lot happening here. What is a transfer learning? Training a neural network from scratch requires millions of images, but what if we could use a network that already learned from millions of images and just teach it our specific task? So MobileNet version 2, you remember using it in module 1.2? This is a pre-trained neural network created by Google. It was trained on ImageNet, a data set of 1.2 million images in 1,000 categories like dogs, cats, cars, flowers, fruits. So that's what we are borrowing here. Okay, and then the earlier layers, if you look at the earlier layers, we are going to be using the simple edges and lines and simple shapes. They are universal, right? They are universal. So we are borrowing the work of the previous people's research. We are adding what we need to add to make our problem solved here. So we are going to run this deep learning approach. Now, see, when you click this, this will go through epochs and then train them. And then it will find only 20 images from our database. But as you can see, there are a lot going on. In step 1 is data augmentation. Okay, so we learned that data augmentation uses the one original image, and it rotates and shifts and zoom in, zoom out, mirror, horizontal, vertical, and then it varies the brightness and fill the gaps with the nearest pixels, and it does all kinds of things to do the data augmentation. And then step 2 is load pre-trained mobile net version 2. As we know that someone did a lot of work in the past recognizing shapes and edges of various things in the world. And we are trying to utilize some of that lessons learned. And then step 3 is fine tuning. And so basically what we're doing is we're freezing the earlier layers, keep universal features, and unfreeze the last 30 layers, adapt to X-rays. Okay, so that's what's happening. And then we're building our own model, and then compile the model and count all the parameters, and then we train and we'll test. That's what's going to do. Interestingly, with only 20 images, it's going to have a hard time. See, in other work we did earlier, the accuracy should just continuously go up. But here, the accuracy is having a little hard time. And then at one point, it even reaches 1 and then goes down, goes down even further, and goes back up, and goes down, etc. As you can see, it's not really doing it with a smooth ride with gradually increasing accuracy. So deep learning result in this case, 45% with only 20 images. That's not surprising. That's not surprising. So that's why it is only 45%. So that's only with 20 images. That's why. So what do? We still want, I mean, if we were to do the real thing, we would feed with thousands of X-ray images to train properly. And then the outcome will be different. So in this case, if we're limited, let's say when you're doing the real project and then you realize that, oh, I want to use deep learning, but it's not really helpful because the accuracy is half or even less than half. That means you can't really use it. And so unless you go out and then grab more data, in this case, images, there are many images in data sets in places like Kaggle. We learned what Kaggle is for earlier. You can go find a lot of X-ray images there with the different diseases all labeled for those images. So what if you can access it, that's great. If you cannot, and then if you still have to work with a limited amount of data, then here's what you may want to do. So what we are going to do is we're going to touch upon the support vector machine. Okay, support vector machine. So the support vector machine here, what we're doing here is that it's a classic algorithm that finds the best dividing line between two groups. Imagine plotting points on a graph. Blue dots for normal, red dots for abnormal. Support vector machine draws the line that best separates them. So for a new image, we ask which side of the line does it fall on? And then it helps us classify either it's normal or abnormal. Okay. Instead of feeding with raw pixels to the model, we calculate meaningful numbers that describe each X-ray. These are things a radiologist might actually look at. Okay, so with a deep learning, learns what to look for by itself. With a traditional machine learning, we define what to look for. We define what to look for. With a deep learning, it needs thousands of examples. With a traditional machine learning, needs only a few examples. Deep learning will have millions of parameters. Traditional machine learning will have features, maybe 24 features. Deep learning is like teaching a baby. Traditional machine learning is like giving an expert a checklist. So since we are limited with the data set, which is a case where you will run into in the future when you're trying to do some system development and you realize that you do not have enough data, and then there's no way that you can get more data, abundant amount of data, then you may have to combine what you have learned in traditional machine learning lessons. Okay, so with only 20 images, it's much easier to learn abnormal X-rays have higher mean brightness than to learn what brightness even is from scratch. Okay, so we're going to run this model here and then see what happens. This will be much faster, just in seconds it finishes. It doesn't go through like multiple epochs like we saw. And then extracting 22 features from each image, extracted 23 features from 20 images, and then support vector machine trained. The result is 85%. Remember, the deep learning had only 45% or so accuracy. Now the support vector machine, the result is 85%. So these features differ between normal and abnormal. Okay, and mean brightness, normal is 132, abnormal 137, median and texture variance. And so abnormal X-rays tend to have higher brightness, more white areas, because when you look at the lung images, there are more white areas. This is exactly what the radiologists will look for, and then they will have their remarks, and then they will label them properly. So what we found out is that, hey, deep learning is great, it's amazing, but the accuracy was so low because of the limited data. And you will run into this in the real world. In that case, you may have to use traditional machine learning or combine them together. And so accuracy here in this case is 85%. That's a dramatic improvement in the accuracy. So final comparison. So we'll compare results between the deep learning with MobileNet version 2 versus traditional machine learning. The accuracy has improved a lot. Okay, so the final results comparison, the support vector machine can identify abnormal lung images much better than neural network. I'm showing you this because this may be a reality in some areas or some industries where you just don't have enough data. Even if you do augmentation and so many different things, and you struggle, hey, how come the accuracy is not improving? I'm giving up. Don't give up. You can use traditional machine learning, and sometimes it does a much better job. Okay, so we know the sheer difference in terms of the data size. So you have to choose the right tool for your data. When you look at the data, don't just go straight to deep learning. Okay, I just got disconnected from the GPU. So here, choose the right tool for your data. If you have less than 100 images, definitely go with the traditional machine learning. Okay, support vector machine or random forest that we learned from module 1.2, use those. If you have data size of 100 to 1,000, then transfer learning, right? And then if you have 1,000 to 10,000 images, then you have to do transfer learning and fine tune. If you have 10,000 plus, train from scratch, go to neural, all right? And the real medical AI requires 10,000 plus validated, clinically validated with labels. And then it requires expert radiologists, annotations, and rigorous clinical trials. And of course, in order to use it for medical diagnosing, then you need a regulatory approval, etc. Okay, so hopefully you learn by looking at different data sizes. You have to make a appropriate decision on how to handle the problem with limited data set. So the final code just runs. It shows you all the answers. The answers may be different because when you run the training model with the randomness added to it, there might be some differences. So don't just copy paste the values here. If you are asked to answer these questions, you have to run it to see the difference. Okay, so hopefully these answers are helpful for you to gain more insights. And then you see when to make decisions based on the data size, the problem you are looking at, the industry you're in. So don't just go automatically to deep learning and try to solve the problem because you may fail. In that case, then you come back and think, hey, what model works best? The traditional machine learning principles and concepts and models sometimes are better. So that's the point that I wanted to make for you so that you will understand this. And so hopefully you picked up some interesting things from here, obviously. It was kind of fun to generate X-ray images with AI. I did not have a time to generate 10,000 of them. If I had 10,000 of them, it would be very much interesting and more accurate, of course. But as you can see, some of the images have just a big circle on the lung. And then the AI claimed that that's abnormal. In the support vector machine here, when you run this analysis, some of them had the weird lung. We can tell it's wrong. Something's wrong with the lung. Although it's wrong, it says normal or abnormal. I mean, it made mistakes. It definitely made mistakes. And so, but the accuracy is 87, 85%. So that's way better than the neural network that we did. So hopefully it was fun. You can replace all these images with other images that you like. It could be objects. You could put images of like stop signs or traffic signals, right? Blue, red, yellow. Or you could have a pedestrian on a street, or bicycle on a street, or truck, or images of cars. And then you can try to classify what kind of accuracy you can get. So hopefully you learned something interesting here, and then hopefully you will be able to apply these lessons when you are designing your own AI model. Don't just go do the neural network from the beginning. You need to analyze. You have to think what data size, what kind of data, and then can you augment them? Can you use existing models like the mobile net? So, don't just get to a conclusion. We need to make an AI model. It's not the right decision. You always need to make sure that you have to see what's available already. What is available? And then what do I have as data? And how much data do I have? And once you know all these factors, then you will be able to come up with your solution, which might involve creating more data or collecting more data or augmenting them. Even you saw from the augmentation with just one photo, you can have 20, 40, 60 different variations by having it resized or magnified, zoomed in, zoom out, change the colors, brightness, or flip it, vertically or horizontally. You can do so many things to create variations. So AI needs variations. and so that it can accurately predict the objects or scenes or animals or features that it never seen before. So, all right, so that's it, and I hope you enjoyed it, and see you in the next segment.